at the university slot. That is the one thing that we are a little bit strict on. It is hard to run asynchronous assignments. So if you're an in-person student and don't have an extremely, extremely strong reason, we expect butts in chairs during the exam slot. Okay, so I accidentally bought a ticket to go home early. Don't accidentally buy a ticket to go home early. We've actually accommodated them in the past, and it just makes for a mess in the TA grading, and then you never know if the solutions get out and stuff like that. Okay? Yes, ma'am?
Get a code to make an account on the
Yeah, sure. I just wanted to double check a few things before I had everybody sign up. Yes. Yep. Mm-hmm. Okay. All right. So keep going. All right. So the last 20 minutes here, 25 minutes, maybe let's go into a little bit more technical material that is perfectly fine if it's new to you, but some of it may be stuff that you have seen. So I like to set the stage for tomorrow or Thursday's lecture. Okay, so sometimes it's kind of useful to think historically about things. And when I was approximately sitting in classes like this, and I was really interested in parallel computing, I actually had professors tell me, why are you interested in parallel computing? Just wait a year for processors to get faster. Right? And so this is a very old plot that Kunle made more than almost 20 years ago now. Of processor performance as a function of time. Okay? And it's a log plot, so you see the exponential. And so you just waited, and Intel would ship their next CPU, and next year it would run your program faster. So you spent all this time taking CS149, you got some skills, and then all of a sudden, your parallel program had to now be even faster to improve over the sequential program. And do you know why that was the case? If we maybe some of the hardware architects in the room. Yes, sir.
Transistor sizes getting smaller.
Transistor sizes were getting smaller, but that's not a direct translation to performance. So you're correct, but you took a couple steps. So transistor sizes getting smaller allowed for a couple of things. It allowed for them to be clocked higher, so frequency could go up. It also meant that more transistors could go on the chip, and architects had to have clever ways to use those transistors to translate into performance. Okay? And in this class, I'm oversimplifying a little bit, but you can kind of think about two major reasons as parallelizing your code for you without you ever knowing it, and two, increasing CPU clock frequency. So this is where I get to a few questions that may seem really dumb, but one of the reasons why I like people writing comments is sometimes when you sit down to write something, you realize that your thinking is not as precise as it may seem. So, look to your left or right, and I want you to spend 30 seconds answering this question. What is a computer program? From the perspective of a computer. Here's definitely a program written in C. No problem. This is a computer program. But from the perspective of a computer, what is this? What is a program? And just go ahead and give that a shot. Spend 45 seconds. What is a program? Can you define it yourself? All right. So someone who hasn't said anything yet, if a talk show host found you on the street while you're walking around San Francisco and they said, "What is a computer program?" You're on camera. What might you say? I just want to see some new hands. New hands. What is a computer program?
A piece of text that can be translated to hardware instructions.
A piece of text. That's a piece of text.
That can be translated.
that can be translated into hardware instructions. And I think that the text aspect doesn't really matter too much. What's important is the back half of your comment is a program is just a list of instructions. Right? So if I take this program, it certainly has a meaning. It has some semantics, and a compiler might get to it. And at the end of the day, whether or not it's a compiler or interpreter doesn't matter, but at the end of the day, a computing machine runs a list of instructions. So here are some examples of x86 instructions that you might have seen. So in CS1, 11, now, like folks.
107
So 7, you've looked at a bit of assembly. This is x86. Most, if you have an Apple laptop these days, it would be ARM assembly. But at the end of the day, all a computer does is it gets a list of commands and it executes those commands. So it's kind of like me making carne asada, which I have to make tomorrow night because I'm out for dinner. I get a list of instructions. I have a set of commands, and what do those commands do? Or maybe another way to ask this question is, what does a processor do? So I'll throw it back at you, talk it over for a second. If I asked you and I said, what does a processor do? If a program is a list of instructions, what does a processor do? I'll let you talk it over for a second. And for those of you that just said executes the instructions, which is a perfect first answer, my follow-up is, what does it mean to execute those instructions? What does executing an instruction do? Okay, let's talk about this. So I heard a lot of people immediately say a processor executes instructions, which is exactly where I wanted you to think about it. And now let's dive a little bit deeper. What does it mean to execute an instruction? What does executing an instruction do?
Either performing a computation manually.
Okay, so it performs some math, like what you did when you came up here. Okay.
Or jump somewhere else in the program set.
Okay, or it jumps somewhere else. Okay. Anybody want to add? I think I can't disagree with any of those. Those are two examples of instructions. Changes a register's value. What are other things instructions might do?
Access memory.
Might read or write to memory. So at the end of the day, we can boil all of this down to instructions perform some operation, like arithmetic or math, and the result of those operations is a change in state. And what I mean by state is either values in memory or values in processor registers. So if I go back, let's look at this instruction sequence here. Oops. Oh, there it was. You see some instructions which are referencing registers, and like moving a value from one register to another is changing the value of the target register. There's other instructions in there when you see the parens. Those are accessing memory at certain addresses and stuff like that. So what I want you to think about, this is a diagram I'm going to use heavily throughout the rest of this lecture and the next lecture. And this is a really cartoon diagram of how to think about a processor. But for most software people, this is pretty sufficient. I like to think about 3 pieces of blocks in any modern processor. One of them, which I'm always going to color orange throughout this class, is about control. Figuring out, it's managing where we are in the instruction stream and figuring out, once I get the next instruction, what do I do? Then I have this yellow box, which is responsible for the arithmetic, maybe adding some numbers or carrying out a move or multiplying some numbers. And I'm always going to call that yellow. And then I have stuff that's blue that's state. And I'm calling this the execution context. It's the context in which we run a program, which is just a big set of values of bindings from register 1 has this value, register 2 has this value, as well as memory has all these values. And the simplest possible way to think about a processor is it determines, given where we are in the program, where we are in the recipe, what to do next. It grabs the appropriate values from registers, it performs some math, and then it updates the value. For example, if I have a simple instruction like add the contents of R0 and R1 and put the result in R0, well, that processor will reference the two, R0 and R1. See how it's in red here? It will do the math. It will compute what? Yes, and what is that? Compute 96, and then it will update the value of, so it gets the contents of those registers, it updates the value, and then it modifies the state of the program to 96. Very, very simple instruction, add. And so for now, I want you to think about this processor as every single clock tick. It's just grabbing the next instruction, executing it, and updating registers. That's all it's doing. Okay? So my review here is hopefully this is review from 107 or 111, is what is a computer program? It's just a list of instructions. What are instructions? They are commands. They are operations to the processor. And those operations are about performing arithmetic or modifying state. And when we talk about state, I'm talking about the values of data in registers or in memory. Okay, there's a question?
You answered it.
Okay, cool. Right? So this program has 5 instructions in it. So it will take 5 steps, 5 processor clocks to execute it. Make sense? Is there any way we could do better? What if I had 2 processors? Okay, this is your program. This is what, let's say I'm a computer and you hand me this program to run. What does this program mean? This program says you must do instruction 1, then you must do instruction 2, 3, 4, 5. That's the order. If I like trying to make my carne asada and I do things out of order, I will be unhappy with the results, right? So the meaning of this program is that the results have to be such that we did these things in this order. But what if we had 2 processors? Yeah.
Do you want to multiply steps in parallel and all the add steps in parallel?
Yeah, so
Or maybe not the add steps.
So you're looking at this and you're realizing that like this multiplication only depends on register 0. This one only depends on this value R1. So, maybe if I wanted to assign work to processors, I could do something like this. Right? And now what can I do next? 3 can go where?
Either side.
Actually, it can go anywhere, right? I'll even put it here because I like processor 2 better. And then what?
Add.
Can I do better?
It can go up.
Right? Because this only depends on 1 and 2, so we can do, and then 5 has to come after 4 and 3. So it's possible for me to do better, even if, even if I have a program that looks sequential because it's written in a line. If you look carefully at it, there's some parallelism there. So the first major, and by the way, you notice what I'm saying is the program says, here's the program. You better compute results that are the same as if you ran them in the order that I told you.